So, so far we have looked at a lot of revision material around algebraic techniques to assist us in this polynomial functions unit. And it literally is that. The skills that we went through over the last couple of lessons are designed to assist you in the graphing of polynomial functions. So just a reminder, a polynomial function is a function with descending powers of, say, x. The lowest, they're all whole number powers, and there's no negative powers either. So, for example, f of x equals, don't write this bit down, the square root of x. It's a function. It's not a polynomial function, even though I can write it as x to the power of a half. That is not a polynomial function because the power is a fraction, not a whole number. Similarly, x to the negative 2, which is the same as 1 on positive x squared, x positive 2, 1 on x to the power of positive 2, but both of those things are equivalent. Neither of them are polynomial functions because it's a negative power. So linear functions, quadratics, cubics, quartics, all of those sorts of things are polynomial functions. Okay, so new for 415 is we can start examining functions that are above cubics. And that's what that bit there means, okay, to the power of 3. So we're going to look at polynomial functions above power of 3, but only in factor form, okay? So we're only going to focus on if I can take say, a quartic, which is a power of 4 function, and I can then turn it into factor form, or maybe you're given it in factor form already, then that's something that you should be able to graph. Okay, and we'll just need to expose you to what it kind of looks like. I'll take you through it towards the end of this lesson. We're going to do a bit of revision first. But I'll give you an example. Good to see some people writing notes down. That's how you learn, isn't it? So I could take f of x equals, I just prepared this little one earlier so I didn't have to muck about too much, negative 2x to the power of 4 plus x cubed plus 14x squared plus 5x minus 6, 5x minus 6. That could be the quartic that you're given. You can use polynomial division and the factor theorem to convert this into something like this. 2x minus 1, 3 minus x, x plus 1, and x plus 2. All of those factors multiplied together. So this is factor form, right? Yeah? This is, I guess, what we would call the general form of the equation, just all written out, expanded. This has been turned into the product multiplication of 1, 2, 3, 4 factors. So that's factor form. So once it's in factor form, I think you should know this already, but I'll go through it a little bit later as well. Each of these factors can be considered a x-intercept or a zero of the function. So that gives us the capacity to graph it because we know where the zeros are. Okay, I'll just give people, there's still a few people that aren't writing anything down at all. That's amazing. Very well done that you can keep it all in your head. But I don't think you're going to learn as well as you can do if you're writing down. So if you want to change your mind and get to writing, please feel free to get yourself organised now. Sonny. Okay, do you want to grab some scrap paper or something? Or do you want to grab your notebook? You can grab it, but I won't wait for you, okay? All right. So what we're going to do, and I'll try and I will be really fast with this, guys. So make sure you do keep up. Again, the notes will be available later. The video will be available later if you need to spin through. But I'm going to do a quick review of what critical information looks like for a polynomial function. Then I'm going to go through quadratic functions, cubic functions, and then finally we'll have a look at polynomial functions above 3, very broadly. So I'll zoom out so you can sort of see all the information at once. Down the back, that's not too small, I hope, to read? Awesome. Okay, so critical information for polynomial functions. Now, because this is review, I'm not going to be doing too much exploration, I suppose, with you guys. I hope it's just stuff that you already know and I'm just reminding you. Please stop me if you think, wait, what now? Kind of stuff. So critical information of polynomial functions. Intercepts. So x-intercepts, y-intercepts, and I might just put this here because I feel like it's new language. Zeros are x-intercepts. So if you see the word zero, it means an x-intercept. So intercepts and stationary points is the collective. Stationary points, and again, get that A in there. Stationary. The AR, like is in car, is stationary on the street. ER, stationary, is like paper, which is paper, ER. So ER for paper, stationary, AR for car, stationary. There are two kinds of stationary points. Who can tell me one of them? Turning point, yep. Calling out's fine. What's the other one? Inflection, yep. Well done. Sometimes you'll see that spelled X instead of CT, but I think everyone here spells it ECT. So in stationary points and inflection points. They're the main ones for what we're dealing with. And the last thing is maybe something you haven't formally looked at. I know in my class I raised that phrase, this phrase. It's called the dominant term. DT. And then I'm just going to put this other word after it, behavior. Dominant term behavior. Now, I will briefly talk about it, but it'll make more sense in the context of polynomials a bit later on. Who's heard of dominant term before? Don't care if you can't define it, just have you heard of it? Yep, cool. So just really briefly, if again, I'll probably put some more formal notes to it later, but in this polynomial here, the dominant term is the term with the highest power of x. So minus 2x to the power of 4 is the dominant term. And we call it the dominant term because, you know, on a graph goes from minus infinity to infinity, right? So on the x-axis. So very, 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 very large negative values of x, either negative or positive, are going to dominate what the function is doing. That's why we call it the dominant term. Like, if you think of a million cubed, just go. Yeah, sorry, I know it's photo day, so if you have photos, just let me know on your way out that you're going somewhere. Em? Negative 2x to the power of 4. Yeah. If you were asked what the order of the polynomial function is, you would say it's 4. It's an order 4 function. But if you're asked for the dominant term, you would say it's negative 2x to the power of 4 because that's the term. So my point is that when let's just take infinity, let's take a million, which is quite a large x value. When x is a million, x cubed is a million cubed, but x to the power of 4 is a million lots of a million cubed. So you can see that x to the power of 4 is much more dominant with the bigger numbers than anything else of a lower power. What that means is that ultimately, when you're looking at really large numbers, whatever's happening in the dominant term will tell us what's happening in the graph. So again, don't worry about why it looks like this, but for that function there, if I've got negative 2x to the power of 4, if I just look at the dominant term and say, okay, what does a really large negative number raised to the power of 4 look like? It's positive, right? Because anything raised to an even power is positive. Then I'm going to multiply that by negative 2. So what's that number going to look like? Negative. So if I'm drawing the graph, I know the graph is going to ultimately start in this quadrant, okay? Where when x is negative, y will also be negative because the dominant term tells us that negative 2x to the power of 4 is negative. When x is really, really big and positive, like a million, what's happening to the dominant term? Well, I'm taking a positive number. I'm I'm raising it to the power of 4, so that'll be positive, and then I'm multiplying it by -2. So that's also going to be negative. So in that particular function, by considering the dominant term, I can see where the graph is going to start and where the graph is going to finish. And then the rest of it is working out exactly what that looks like for the rest of it. Okay? But what you can't have is like that. This dominant term theorem works for all polynomial functions, including quadratics, including cubics. It's consistent across all of them. It's just that in quadratics, you learn a basic fact, and that is look at the value of A. If A is negative, it's a frowny graph. If A is positive, it's a smiley graph. But that's effectively dominant term utilised in a very specific instance. Okay, I'm probably going a bit too slowly. I need to speed up. Does anyone have any questions? Okay, let's have a look at quadratic functions. You should be very familiar with quadratic functions by now. So I'm just summarizing the forms of quadratic functions. So you've got general form. Now, general form is when I'm just going to do an example, is when you've got it in the form ax squared plus bx plus c. So, for example, 2x squared plus x minus 1. Sorry, I'll get out of your way. 2x squared plus x minus 1 is an example of general form. The other form is factor form, sometimes called intercept form. For what I hope is obvious reasons. F of x is equal to 2x minus 1 multiplied by x plus 1. Okay, general form, easy to find the y-intercept from that because it's c, -1, or 0, -1 to be precise. Factor form, easy to see what the intercepts are. So for that one there, the intercepts, or the x-intercepts, I should say, are a half and -1. Is that okay with everyone? Take each factor, set it equal to 0, and solve for x. So it's a half and -1. What's that third form called? Starts with turning, ends with point form. Hey, turning point form. So turning point form is the third one. I might do that on the next little slide across there. I'll just say TP form, and I think you should know by now what that means. And I'm just going to really quickly do one just to remind you of how to do it. And because I think the way I do it is slightly different from the way others do it. So, obviously I've got the best way of doing it and everyone else is just second rate. Yeah, okay. So we'll go with that. Yeah, particularly your dad. Goes without saying. 2x squared. So I'll use the same one, 2x squared plus x minus 1. And I've deliberately chosen one that isn't particularly straightforward just to illustrate what's going on there. So f of x equals 2x squared plus x minus 1. So to change that to turning point form, first of all, I isolate the a value, in this case 2, whatever the coefficient of x squared is. And what I do is I take the a value outside, and I use square brackets just to differentiate it from what's happening inside. It'll make sense as I go along. They're not magical, it's just a different shape. So 2, so if I take 2 outside of, inside the brackets, I've got x squared, because 2 times x squared is 2x squared. And then I've got plus a half x. And I'm going to close the bracket. Minus 1, and the minus 1 is, I'm not factorising that out. So I'm leaving the minus 1 all by its little lonesome there. That's what I do differently to other people, I think, because if you remember from turning point form, you end up having to expand it all the way through anyway, so why bother doing it? So 2 multiplied by a half x will give me the x that I had to start off with. So these two are equivalent expressions with this partially factorised start. Then I complete the square in the middle. So just to remind you, you go 2, there's a 2 there. Now, completing the square means I go x, and then I halve the b value here. So b is a half, so I halve it. So that is a quarter. A half of a half is a quarter. Close the bracket and square it. And then I immediately subtract this squared. Now, again, in 315, I go to great pains to explain why this works. And, if you expand it, you can see it happening for yourself. I'm going to assume that that's as a given, that you understand why this works. So if I subtract a quarter squared, I'm subtracting a 16th, and then I've got -1 at the end. Now, again, just to remind you, if this was a minus x in the middle, this would be a -1/2 here. This would be x minus a quarter, but you always subtract here regardless of what's happening in here. So it's always minus this number squared. Okay, so a quarter squared is a 16th. Now I'm going to expand those square brackets, and that gives me 2 outside of x plus a quarter squared. 2 times a 16th is an 8th. I'm just cancelling down the 2 and the 16 to make it 1/8. And right now, I think just to save myself time, I'm also going to convert that 1 into 8ths as well, because I know that's what I'm going to have to do. So we've got -1/8 minus 8/8. And that gives me a final line of turning point form of 2 outside of x plus a quarter all squared minus 9/8. And that is turning point form. Yeah. Yeah, I did times it in this step from here to here. 2 multiplied by 1/16 is 1/8. Because I didn't factorize it to start with. Yep. And that's why I do it. If you factorized the whole lot, then you would have had -1/2 here inside the bracket, and then you would have expanded it, and then you would have got back to this step anyway. Yeah. That's why I think my way is a bit more efficient. Just factorize the first 2 terms, not all 3. Try it for yourself. If you're used to factorizing out all 3 terms, try it for yourself. It might feel a bit unusual, but with practice, it is much more efficient. So turning point form, again, obviously tells us exactly what the turning point is, which is, what is the turning point in this instance? -9/8 is one of the coordinates, but a turning point is a pair of coordinates. Yep. Close. -1/4. Yep. So it's x minus h all squared plus k. So that would be -1/4 minus 9/8. So the turning point's given to you beautifully in this one, but nothing else. Everything else has to be worked out. The y-intercept has to be worked out. The zeros have to be worked out from there. It's always the same process, though, and this works for all polynomials. I'm not going to write this down. I'm just going to verbalize it. In all instances, the y-intercept is worked out by setting x equal to 0 and solving. The x-intercept, or zeros, are worked out by setting y equal to 0 and solving. That's how you always, doesn't matter whether it's a polynomial function or anything else, all functions can do work the same way. You substitute in x equals 0 or y equals 0 to work out the intercepts. Alrighty, any questions? Okay, in this one here, again, because I'm just summarizing for you, and we actually did something like this at the start in our first lesson, I think. Let's just sort of function from working out the function from the graph. This is just a summary. So working out the function from the graph, you've got 2 scenarios. You've got either something like this, where you're given 1 point and you're given the turning point. So you start with TP form and then go from there. Or you're given something like this. I might just zoom up on that just so you can see it just for this little bit. You're given the intercepts and you'll start with intercept form or factor form. That's really squishy there. Sorry about that. And what you're almost always doing the name of the game is to find A. The dilation factor is almost always what you're doing. Okay, so typically, for example, you put it into turning point form, A outside of x minus h plus k all squared. That'll give you the form of it, except you don't know what A is. Then you substitute this point in for x and y, and then you'll work out what A is, and that'll be it. Or you're given the intercepts like so, and maybe the y-intercept or something else. I didn't write that down, but I should have. And one other point. And once you've got that information, you can substitute in. That's terrible. I'm going to just fix that while I'm thinking of it. It won't be A comma B. It'll be A comma what? 0, right? It's an x-intercept. And then this would be B comma 0 for something. Okay, it's an x-intercept, so y is always 0, right? So it's A comma 0, B comma 0, plus one other point here somewhere. You'll be given one other point somehow. And what they can do is they can make the other point the y-intercept, for example, or something else. Now, there are other situations. You might be given 3 points on the graph and you have to use simultaneous equations to work it all out, that kind of thing. So they can make it more complicated for you. But basically, they give you a certain amount of information, and then you need to use one set of the information to come up with a basic form, and then use the other bit of information to work out the dilation. So in this case, you would use turning point form to create the initial graph, and then use the other point to work out the dilation, A. This one here, you'd put it into factor form or intercept form, so x minus A times x minus B, and then you would substitute this point in to work out the dilation, okay, the A. Because you've done all this before, I know that's really brief, but is that making sense to you so far, or reminding you at least? Does anyone have any questions? I'm about to set you to do some work for a bit. Okay, I'm just going to pause the video. The next bit is cubic functions. Okay, this will be faster than the quadratic stuff. I should point out straight up, and I haven't got this in my notes, is just like in 315 last year, for quadratics, we can definitely ask you to work out where the turning point is, because there's a form for it. For cubics and above, you won't be asked to work out the turning points in the functions unit unless it's a cubic in turning point form, I guess. But you may be asked to do it in the derivatives unit, in the differential calculus unit. It's one of those silly separation of content which doesn't make sense in the real world as much as this is the real world. But because we are ratings based, the criterion for polynomial functions is not the same as the criterion for differential calculus. So differential calculus is how we work out stationary points for cubics and above, except if it's in cubic form. In turning point form. Okay, so I'm just going to focus on the forms of a cubic function. So forms, there's really two forms for a cubic function. I'll get out of your way. So again, when I write this form down, it's this actual form could be anywhere on the graph, on the axes really. I'm just going to put it here, like so. But that line could be anywhere in the plane, in a Cartesian plane. Okay, I've got it there, but it could be anywhere. So this is of the form y equals A outside of x minus h all cubed plus k, and hk is the inflection point. Okay, it's a stationary point. It's not a turning point because the graph doesn't change direction, but the graph gets slower, stops, and then starts again. So it inflects at that point rather than turns at that point. okay, h comma k. So if you're given a function that's an inflection, if you're given the picture of a function, and then you're asked to write the function, that's reasonable. Or if I give it to you in this format and ask you to draw the graph, it's reasonable for you to be able to identify where that inflection point is. Is that okay? The other form is like this. By the way, I'm only doing like a positive left to right kind of graph. That graph could be inverted. We haven't talked about transformations again, but we are going to talk about transformations. That's a threat. But yeah, there are transformations that can apply to all of these graphs. So then we can have a roller coaster graph like this. Like so. So that's a function of the form. I'm just making this up. 2 outside of x plus 4, x minus 2, x minus 3. Okay, that's, what I've drawn there is not that, but that's what I mean. It's in factor form already. I can expand that into general form, but I'm just looking at the shapes of the graphs, not so much the functions themselves. But then we've got a third thing we could get. Can anyone remember what the third one kind of looks like? I don't just mean a roller coaster, but backwards. Yeah, I think that you're describing it. Yeah, good. Do you remember that? So you can get it looking like this. Again, I'm just doing left to right, but it could be upside down. So it bounces like so. And what does that mean if it bounces? Double what? Double what? Double intercept or double root, they often call it. So it looks like this. And again, this is just an example that I'm just making up. X plus 1 multiplied by x minus 2 all squared. Or it might be x minus 2 multiplied by x minus 2. That's where the double comes from. It's a double intercept, a double zero, double root. All of those things mean the same thing. If it's a double, then it's going to bounce. If it's a cubic, it's going to inflect. Any questions on that? What have we got? We've got 8 minutes left. Okay, so I'm going to stop the video here and I'm going to look at higher order polynomials at the start of next lesson. We've got about 8 minutes left in this lesson. I'm going to get you to do a bit of cubic work. Again, this is all just supposed to be quick revision. And then at the start of next lesson, I'll go through higher order polynomials and just discuss the theory behind that. It's not that tricky, don't worry. So I'll just stop the video.